Okay, welcome everyone. So today we'll be talking about physics. Thank you all for coming. I'll be your teacher for today. My name is Benjamin Wright. I'm going to go to MIT in the fall as a freshman. I've been doing math for a while. You've probably seen me with some other classes for Math Divulged. I'm excited to have you. Today we have Kevin Chang as our TA, and Brian Liu is here to help as well. So direct your questions to them. I probably won't be answering them because I'll be busy, teaching the class. So, okay, so here's a basic outline. We'll first be going over some basic physics to give you the foundation to understand what we're going to do. And afterwards, we're going to go over some proofs. So a lot of them will just be using physics to prove math. But depending on how you can think of it, you can flip the directions and in fact use math to prove physics. It's really just a matter of perspective. So I'll be presenting a lot of them as using physics to prove math, but you should really keep in mind that it can go either direction. Okay, let's get started on the physics. So one of the most fundamental concepts of physics is force. And force is when you push or pull on something. So if you have your hand and you push on a box, then you're exerting a force on it. And in this diagram, you'd be exerting a force to the right. And we represent this force with this arrow here. It starts from the center of mass of the object, and it goes in the direction that you're pushing on it. And if you remember from a previous class, depending on which classes you've been to, this thing over here is called a vector. A vector is just an arrow. It has a length and a direction, and it doesn't really have a defined starting point. So forces are just like that. They have a direction, like which direction you're pushing, and they have a length, which is how much force you're exerting. You can have stronger forces and less stronger forces. So oftentimes there are multiple forces acting on an object. There can be gravity, there can be you pushing, there can be someone else pushing, there can be friction, etc. So physicists draw diagrams called free body diagrams. And these diagrams are essentially a bunch of vectors drawn from the center mass that represent all the forces exerted on an object. So in here, I drew 4 vectors. There's a force from gravity pushing the block down. There's a force from the earth that's pushing the block back up. The hand is pushing on the block to the right. And there's a small bit of friction from the rough surface that's resisting the push of the hand. So it's very common, you'll see like 4 forces like this. And when you have a lot of forces, the concept you're most interested in is net force. And net force is the sum of all the force vectors. You can think of it as like there's just multiple pushing and pulling, but in the end, once you add up everything that's happening, there's one total push or one total pull that the block is being subject to. So if you look in this this middle example, the top and bottom forces are the same, but they're opposite. So they will cancel out in the net force. And then the friction, the left arrow would remove some of the impact of the right arrow. So the net force would be this green arrow, something like this. And the net force is the most important concept for determining how the block will actually move. And the way we do that is through Newton's second law, which is F equals ma. And this is a theorem you'll see everywhere if you take physics or have already taken physics. To be more specific, net force equals mass times acceleration. Acceleration is the change in velocity over time. So if you guys took the calculus class, you'll realize that acceleration is the second derivative of your position with respect to time. If you don't know what this calculus symbol means, you just have to realize that you just have to think of it as velocity is your change in position over time, and acceleration is your change in velocity over time. So you're doing two of that change in something over change in time actions. Okay, so very often if you have a constant force, like you're pushing at the same like effort, then the object will start to accelerate. Okay. If this was a pure, like if this was like a physics class in school, I would probably go more in depth and give you a more intuitive understanding, but we kind of have to go quickly. So I'm just going to breeze through this. Okay, next there's a concept of pressure. So when we exert forces, we're usually distributing the force over an area. It's very rare, like it doesn't make much sense for you to have a large amount of force through just like one infinitesimal point. When you have a hand, which I'm going to draw like this brick, there is this whole length that turns out to be the area of your palm that you're exerting force upon. And if you want to examine how much force a certain part of your palm exerts, you have to use the concept of pressure, which is defined as the force per unit area. So you can think of it this way: the force over a region is equal to the pressure, which is P, times the area. And this is true under constant pressure. So if each part of your palm is exerting the same effort, then you would say it's constant pressure. This is probably not actually the case. Like the base of your palm will probably have more pressure than the tops of your palms. But this concept is more applicable when you have air that's exerting force on an object, or water that's exerting force on an object. Water and air doesn't always have the same pressure, but it's pretty common for them to. Mostly air. If you have a box in midair, you actually have air exerting pressure on all sides of the box. It just turns out that if you have a box that's completely surrounded by air and all the air is the same pressure, the pressures kind of cancel out and your net force from the air is mostly zero. At least in the ideal world, if you have a block actually falling or moving like an airplane, you'll actually be pushing some air, so there'll be areas of higher concentration of air and areas of more vacuum type air, and that will cause a change in pressure, which means that you can't just ignore air anymore. Okay, so that was pressure. So now I'm going to introduce a more advanced kinematics topic, and that's torque. Torque. Torque is a method physicists use to calculate whether when an object should rotate based on forces. The most common example used to define what torque is, or give an idea about it, is if you have a door. We're looking at a door from top down. So we have a pivot here, which is a point that can't move. And then we have the rest of the door. So you can swing the door backwards, like over here. But no matter how much force you exert, this pivot point at the very left will not move. So how do you determine how the door moves? Well, if you know from real life experience, if you push at the door near the pivot, like this, it's going to be very hard to open the door. But if you push at the door near the edge, the door swings open more easily. And from this, we can determine that rotation is more effective if you're pushing farther away. And torque is kind of a number that represents how much rotation you're giving it. That's a yeah, that's not a very formal definition of torque, but it's a more intuitive one. So the actual formula for torque is your radius times your force times sine theta, where theta is the angle between your radius and your force. So in this door example, your radius will be the length will be this green length, from the pivot to the hand force. The F will just be like how hard you're pushing on it with the hand. And theta will be 90 degrees for this example because you're pushing at a perpendicular to the radius. And this should make sense because if you're kind of pulling the door, let's say you have this yellow hand and you're pulling the door directly away from the pivot, it wouldn't make sense for the door to actually swing. The door just won't move. And this is an example when theta is equal to 180. So sine of theta equals 0. So the torque is also equal to 0. So the angle at which you apply the force really matters. Okay, so the torque is one of the first places that physics becomes really cool, in my opinion, and becomes kind of math-like. Because you have vectors, you can represent this in more math notation, which is R cross F, where cross is like a math function for two vectors. So there's a mathy way to deal with torque, and some really cool like manipulation you can do. One way that the math is cool, or that torque is cool, is if you have a pivot right here, and you have a force that's exerted at this angle, and your radius is this way. So here, your radius and the force are not at 90-degree angles. So some of the torque is lost from the sine theta. Well, if you use trigonometry, you realize that if you drop a perpendicular to the force, so this length is R, let's call this length D. Then our torque before was R times F times sine theta, but that's actually equal to D times our force. So you can regain that perpendicularity by just dropping altitude. And dropping altitudes is really nice. But you can also drop a different altitude. You can drop this altitude to make the force perpendicular. And what should we call that? I'm just gonna call that G. So this is also equal to the log R times the part of the force that's perpendicular. So torque, you can either just use sine theta, you can use the math cross product, or you can draw perpendiculars in two different ways. So there's all these different ways of managing torque that allow us to do some cool manipulation. Torque is a pretty hard concept to understand, so you may have trouble here, but I guess I'll just ask you to trust me on this. Okay, we still have energy to talk about, but I think I'll just go ahead with some proofs and we can go back to energy once we start to encounter energy. Okay, so the first theorem we're going to talk about is the Pythagorean theorem. Historically, the Pythagorean theorem has been proven many times in many different ways, with mathematicians constantly trying to aim for the most elegant proof or a fastest proof for the Pythagorean theorem, etc. And we are no different. We're going to have some pretty cool proofs of the Pythagorean theorem involving physics. Yay. Of course, as I said earlier, you can either view this as proving the Pythagorean theorem or using the Pythagorean theorem to prove some physics concepts. So we're going to directly apply torque in this example. So imagine that we have a triangle and we fill it with some gas of constant pressure. Like we can just call it air. And let's say it's in space. So outside it exerts no pressure on the triangle. So we just have a triangle and we have an air inside of it that's trying to like burst out of its seams by exerting a pressure. So if you can imagine this situation, there's an assumption. And this is the thing that you would be proving if you go in the reverse direction. The assumption is the shape does not move. And this is part of a bigger like assumption / theorem, which is if you have a shape and you place it under, you completely surround it, or the inside is completely filled with a constant pressure source, then there will be no net force exerted on the shape. This kind of seems intuitive, right? Like if you put an object in like a liquid or something, it's not going to suddenly start rotating. Like that wouldn't make any sense. So this is a very intuitive concept, but we can actually use this to prove the Pythagorean theorem. And the way we do it is I'm going to set a pivot up here, pivot. So that top blue point can't move. So our triangle is just rotating around that pivot. And let's call these lengths A, B, and C. So the fact that there's no rotation means that the torque, like there's no rotation over a long period of time, which means the torque must be 0. We must not be exerting any like rotational force on it. So this implies torque equals 0. And how do we find the torque acted on this triangle? Well, the total torque is just the sum of the torques on the three sides. So this is torque on side A plus torque on side B plus torque on side C. Okay, and now we get to the tricky part, which is calculating the torques on the three sides. So I'd like it if you participants, could try your hand at calculating the torque, the impact of torque on the three sides, and give me a result. It'll be easier if you know calculus, but you don't really have to. I'll give you a couple minutes. First, try your hand at finding the torque on side A, on this side. If it's too hard, you can say that as well, and I can just give the proof. Okay. Okay, someone said too hard, so I'll just go with it. Okay, so the way torque works is the red dots, which is the gas, is exerting torque on the sides. The sides aren't exerting torque on each other. Or if the sides are exerting torque on each other, it kind of cancels out. This is another really cool thing about physics, which is if you have an object, like parts of the object exert impacts on the other parts of the object, but we can usually ignore those as physicists. Like internal forces, as we call them, kind of cancel out. And the same is kind of true with internal torque. So in most cases, you don't have to consider the impacts of parts in the object and the other parts of the object. So there's no torque of B on A or A on B. Like we don't need to consider them. Okay, let's calculate the torque. So if you remember, torque is your radius times your force times sine theta. So if we look at side A, we have a bunch of forces, or kind of like another word for pressure, exerted all along the length of this. And pressure is exerted at a 90-degree angle, like air just pushing directly against it. So we can actually ignore sine of theta for now, for this side. So the troublesome part about calculating the torque on side A is that the radius changes. Like the radius early on is like 0, and later on is that gets to the full length of A. So it's very hard to directly apply this. And in fact, you can't directly apply this. What we're going to have to do is we're going to have to break this line up into multiple smaller segments. And each segment will give us a little bit. So a segment at length h away gives how much torque? Well, the radius is just h. And the force, how much force is given? Well, if you remember before, I said that pressure is just, force is just pressure times the area of the region. And here we're doing 2 dimensions, so we can just talk about linear length instead of area. So this is pressure times the length I haven't actually set the length of the segment yet, so I'm going to call the length of the segment this DH thing. DH is a common, D of something is a common thing in calculus. It just means a small change in what H is. So H is the height, so a small change in the height gives you like a segment of the length. So H times P times DH is the torque a small segment gives us. So how do we sum up all of these? Well, summing up a lot of really small things is exactly what calculus does. So you can directly apply calculus to this and get the answer. And that would be integrating H times P times DH. If you know calculus, that's good. I'm going to assume some of you don't know calculus. So in that case, we can think about it this way. So H times P times DH is linear, and it increases proportionally to H. So if we graph the torque given, the torque given by the segments, or to be more specific, I'm graphing the change in torque over a change in H, I think. So we'll get some line like this, where this line is H times P. What we're doing is we're summing up a lot of really small rectangles here. And each of these rectangles has side length DH. And each of the heights of these is H times P, where H is changing. This x-axis is H. So we want to sum up all of these red rectangles. And another way of doing that, instead of finding out each rectangle, we can just find the total area under the curve, under the line here. Because all the rectangles will cover up all the area of this triangle. So how do you find the area of a triangle? Well, it's 1/2 times base times height. So the base is like the range of H values, and H goes from 0 to A, because A is the length of the original segment. So the base is A, and what's the height? Well, the height at any point is H times P, so the height at the very end, or the height of the triangle, is A times P. So this just gives us 1/2 A squared times P. Okay. So the torque exerted on side A is 1/2 A squared times P. So we can do a similar thing for the torque exerted on C, which is 1/2 C squared times P, because sides A and C are the same thing. They're just a length extending from the pivot. So we can apply the same process to it. So I should add a negative sign, and I'm adding a negative sign because it's in the opposite direction of A. The torque on A is pushing it. Or if I was to be really rigorous, I would put a negative sign in front of the torque on A. And that's just because by convention, we put torque pushing something counterclockwise is positive, and pushing something clockwise is negative. Because they're in opposite directions, so we need a negative sign. Okay, now the only thing we need is the torque exerted on side B. And we're trying to prove the Pythagorean theorem, but you can kind of imagine that we know what we're trying to prove. We know what the Pythagorean theorem is. So you can recognize already that if our end goal is total torque equals 0, well, we know that we already have 1/2 C squared P minus 1/2 A squared P, and then we add the torque on B. Since C squared equals A squared plus B squared, like we really want this to be 1/2 B squared P, or negative that. And if that's true, then this would force C squared to be A squared plus B squared. So essentially, we want to be able to apply the same exact formula to B. But how do we do that? It's hard, right? Because B is not actually touched to the pivot. So won't R start at A? So R will start at A and it'll go to C. And that's not 0 to B. So this makes us sad because we can't do the same 0 to A, 0 to C stuff as you did before. Well, it turns out we actually can treat it the same way. And the reason why is one of the parts of torque that I said was cool earlier. If you remember from torque, when we had a force that's not 90 degrees, we can or when we had a force that's not 90 degrees to the radius, we can draw perpendiculars. Like we can use this radius instead of the actual radius, and we can get rid of the use of sine theta. So if we apply this to this example, our radius will be something like this, radius, and our force will be something like this. So if you note here, the blue vector and the orange vector are not at 90 degrees. So we can actually apply this taking a perpendicular. And how that works is the perpendicular will be here. And if you note, this green vector, actually starts at 0 and makes its way to B, because it just goes along the line parallel to side B. So using this green vector, it's exactly the same as the other sides. So we get 1/2 B squared P, and plugging that into our equation over here, since torque is 0, this gives us C squared equals A squared plus B squared. So that completes the proof of the Pythagorean theorem. This. Yay. Okay. If you guys don't really understand torque very well or don't know calculus, it may be kind of hard to understand this. But I think this is a very beautiful proof, in my opinion, because it reconciles torque, a beautiful math theorem, and a very intuitive physics principle that's kind of hard to prove. So you can actually use this theorem to prove the principle. Like if you go in reverse, you can prove the principle that for any object, if you submerge it in air completely, it'll experience 0 net force. And you can prove that with this by turning any side into vertical and horizontal sides. So if we have a random shape, like a polygon or something, we can go reverse, and we can turn any of these diagonal sides into just a bunch of horizontal and vertical sides. And once our shape is changed into a bunch of horizontal and vertical lines, it's really easy to prove that there's no net force on it, and no net torque on it, because you can easily match horizontal forces. It's much, instead of adding a bunch of diagonal forces in random directions, a bunch of horizontal forces and a bunch of vertical forces, it's easy to see that they cancel out. So that's how you would prove the still principle. I don't know the actual name for it. We're not going to go over any proofs that are pure math. We're trying to use physics stuff here. Oh my gosh, I have so much to show, but not enough time. in case I don't get through all the stuff I want to go through today, a lot of this is shown on the book, The Mathematical Mechanic. And this book shows a ton of ways to use physics to prove math theorems. And I recommend you go check it out. It starts to get pretty more intense later on in the book though. So we're kind of just going over the starting parts of it. Check it out. Okay, let's get into the topic of energy now. Energy. What is energy? Energy is, you can think of it as like a measure of the ability of an object to do stuff. So there are different types of energy. There's kinetic energy, which is an object moving really fast. And since it's moving fast, it's able to do stuff because it has speed. Like an object that's just sitting there, it can't really do anything because it doesn't have the speed to do stuff. That's one type of energy, which is kinetic energy. There's potential energy, which is if you have like a spring and you push the spring together, the spring it has the potential to do stuff. Like if you release your hands on the object, the spring can push the blocks, and that turns the potential energy into kinetic energy. So there's a fundamental theorem in physics, which is energy is conserved in isolated systems, and total energy in the entire universe is conserved. And energy does not get wasted. It just turns into other forms of energy. So potential energy can be turned into kinetic energy. Potential energy also can exist as height. So falling down a certain height will give an object kinetic energy. Therefore, height itself is a form of potential energy. So this is gravitational potential energy. Even when you think energy is wasted, it's really just being turned into heat, which is giving speed to a bunch of tiny air particles. So heat is also a form of kinetic energy. Okay, so you may be wondering, how are we going to use energy? When is it useful? Well, there's a tendency of systems to seek out situations with the minimum potential energy. So if you have an object in the air, it'll fall down. It'll seek a lower gravitational potential energy. If you have a lost spring, it'll try and release this potential energy by pushing on the blocks. So any system will try and get to a minimum in potential energy. And we can do stuff with that. First off, we can once again prove the Pythagorean theorem. With a cool setup. We have a block on a semicircle. So the block has like a hole in the middle of it. So you can slide it along the semicircle, but it can't move anywhere else. It has to stay in the semicircle. And then you attach springs from the sides. So let's call this side length A, this side length B, and this side length C. Can you guys see where this is going? Okay, because this is a semicircle, we know that this angle has to be 90 degrees. So how are we going to show that the Pythagorean theorem is true? Well, the first thing we note is, well, we want to, I kind of have to explain some stuff about springs before I do this. Sorry, my bad. So if you have a spring and it's pushed on an object, the force is a constant K times the change in distance. So there's usually like a normal length for the spring where there's no force. And then if you push it past that length, then the spring starts exerting a force in the opposite direction that you push it. And that change in distance is proportional to the force. So in this problem, these springs have 0 rest length. So that means the force is literally just K times A, or K times B for the other spring. These forces are in different directions, remember. And there's one more thing I have to explain, which is the potential energy of a spring. If you have a coiled up spring, the potential energy, like the amount of kinetic energy it can give, is equal to 1/2 K times delta x squared, where delta x is again the change from the rest length. So the total potential energy of the system is 1/2 K A squared plus 1/2 K B squared, because we have the potential energy from the two springs. There's no gravitational potential energy because I'm imagining this laying flat on the table, so don't have a change in height. So if you notice from the Pythagorean theorem, we have a squared and b squared here. So we know this will end up being 1/2 kc squared, which is a constant. Well, we don't know that the Pythagorean theorem is true yet. We're trying to prove the Pythagorean theorem. So we actually don't know it's constant yet, but we want to prove it's constant. And proving that potential energy is constant is actually equivalent to showing that there's no force on the object. Remember, systems want to get to lower potential energy. So if the potential energy is the same everywhere, the system feels no need to go anywhere, because it can't fall to a lower potential energy if everywhere is the same potential energy. So nothing happens. So we just need to show the net force is 0. So how do we show the net force is 0? Anyone? Does anyone have an idea? Yeah. How do you show it doesn't move? To do this, we're going to have to go back to the very beginning, where I talked about forces as vectors and adding up the vectors. So if you have this object, so if you have the object, we have one force from the left spring with a length K times A, and we have another force from the right spring with a length K times B. So we just have these two forces can't cancel out, but we realize that the object can't actually leave the semicircle. So its only possible motions are in these two golden arrow directions. So it turns out that if there's no net force along this golden axis, there actually will be 0 net force total, because the semicircle, which you can imagine as like a band or like a semicircle of metal, the semicircle will exert a force to cancel out any force that's not along this golden axis. So we just have to show that summing up these two black vectors is perpendicular to the golden axis. How do you do that? Well, vectors don't actually have a starting position. Remember how we said earlier, vectors only have direction and length? They don't have a starting position, which means we can actually move this second black vector to be over here. So adding these two vectors now means following the black and then this blue vector. So the sum will be this green vector. So this is the sum. So how do you show that this green vector is perpendicular to the golden axis? Well, we can return to the original diagram here. The green vector in this case is here. And the golden axis is tangent to the semicircle like this. So to show that the green axis is perpendicular to the golden axis, all we have to note is that this green arrow actually passes through the center of the circle. And why is that? Well, we actually form a parallelogram here, even though it doesn't really look like it. This is a parallelogram. And a parallelogram means the diagonals bisect each other. So this and this are split in half. And remember, in a semicircle, the diameter, when you split in half, you get the center of the circle. So the green vector passes through the center of the circle, so it's perpendicular to the golden axis. And that proves everything we need to prove. And yeah, it's a parallelogram. It's also a rectangle because of the 90-degree angles. But for the split diagonals, it only needs to be a parallelogram. It's just nice that it happens to be a rectangle. Okay, so a quick outline of this proof again. From our concept of potential energy, we wanted to show that the total potential energy is constant. And to do that, we needed to show that the diagram doesn't move. To show that the diagram doesn't move, we need to show that the forces exerted on the object won't move it along the semicircle. So we had to show that the forces add up to perpendicular to the semicircle. Okay, yeah, Kevin posted a summary. So I'll let you guys read that if you're confused. I got to, I do pick just a couple of the really cool proofs. Which one should I do? So there's a concept, there's a theorem in math called the Fermat point theorem, which is if you have a triangle A, B, and C, and you take a point P, if P minimizes PA plus PB plus PC, then P is called the Fermat point. This will be, for example, if you have 3 cities and you need to have a distribution center that sends out water or something to the 3 cities, and you want to minimize the length of road you create, perhaps to save money or not harm the environment, whatever. So in this case, an engineer would pick the Fermat point between the 3 cities to minimize the total length of road created. Okay, so that's a Fermat point. So P is a Fermat point. The theorem is the Fermat point actually satisfies the conditions that the angles, these angles, are actually all equal to 120 degrees. There's some cool math proofs with cyclic quads, and you should really check it out. It's really cool. But I'm going to go over the physics proof. And the way we're going to do that is we're going to place this on a table. So imagine like a triangular table with legs, and it's sitting on the floor. So now the triangle is horizontal, so there's no change in length. I'm going to install pulleys here. A pulley is a system where you have like rope that goes over the pulley, and then the rope goes somewhere else, maybe to another pulley or something. And I'm going to attach those pulleys to objects. And then I'm going to connect the ropes together to this point. So we have 3 pulleys, we have 3 masses being pulled down. Each of these masses has constant mass m. And we let the system go to an equilibrium. So we let P shift to a place that it would kind of settle towards normally. So if you remember before, I said that systems try and aim to minimize potential energy. So the equilibrium point for P will be a place where the potential energy is minimized. Equilibrium, let me write it down. Minimizes potential energy, which in this case is just gravity. So to minimize gravitational potential energy, the system wants the masses to be as far down as possible. And this is why this tells us that P actually minimizes AP plus BP plus CP. And it minimizes these 3 lengths because the least length it has of rope that's on the table, the most rope is actually contributing to lowering the masses to the ground. The more rope you have below the table, like the farther down the masses can be. So P has a really strong incentive to minimize the amount of rope above the table, which is just a Fermat point. Okay, so now we know that the equilibrium for this situation is the Fermat point. So how do we show that it has a 120-degree angles? Well, there's a second theorem we can apply, a physics theorem that we can apply to equilibriums. And the equilibrium theorem is that net force must be 0 in equilibrium. So if you look at this point P, we have 3 forces applied on this point P. And those forces are forces from the strings. Like a string just has a tension force in it. The material pulls along the direction of the string. So we have 3 forces applied in these 3 directions. And then the magnitude of these forces is equal. The magnitude of these forces is actually mg. This is because the force of the string needs to be just enough to perfectly pull up the weight of the masses. Since the 3 masses are the same, the forces in the strings in the 3 strings will be the same because they're supporting the same mass. So we have a point P and we have 3 forces that are the same. And we know that the sum of these 3 equal vectors must be 0. It turns out that to do so, these 3 angles all must be equal. That's the only possible way for this to work. You can try and think of why by yourself. Like if you have 3 vectors, like this, then they'll sum up to like a really big vertical vector. To more rigorously prove it, if you have 2 vectors of the same length, then adding the 2 will get you a vector in the middle. So to cancel out that vector with another vector, you need to have that 3rd vector be in the exact opposite direction. So that by itself requires the 3 angles to be 120 degrees. Okay, that proves it. Yeah, essentially, the cool part about this is we use 2 different theorems about equilibrium in physics. And the 2 theorems were the theorem 1 is equilibriums minimize potential energy. And the second one was equilibrium has net force equals 0. And before, we also used equilibrium has net torque equals 0. So we have all these physics theorems about equilibriums, and that's like one of the really powerful things about physics that you can apply to math, which is, like in math, sometimes it's kind of hard to define what an equilibrium is, but the concept of an equilibrium in physics is very clear. Like stuff just like isn't moving, it's not changing. So you can do a lot of stuff with it. We don't really have much more time. Okay, which one should we do? Okay, let's do, should we do a vote? Okay. Okay, let's do this. So we don't have much time, so I'm going to do another. I'm going to introduce a theorem in math called Mamikon's sweeping tangent theorem. Okay, what this theorem is if you have like a region, if you draw a lot of like tangent lengths, then if you can rearrange the tangent lengths to have the same pivot point. So here the points are moving along. If we merge all the red points to the same position, then we get this new region. And it turns out that these regions are actually have the same area. This is Mamikon's sweeping tangent theorem. Mamikon. Okay. Please don't spam raising your hand. It shows up. I'll make this quick. Okay, so a concept in math is the tractrix. So if you have a point 1 unit above, and you have this rod of length 1, and you grab this bottom point and you pull the bottom point, then this point actually, the top point goes in a direction like, goes in the path like this as you pull the green line. This is called the tractrix. Yeah, okay, we'll finish within like a minute, I think, or maybe 2 minutes. So it's, if you want to find the area of this in math terms, you have to go through a really long process where you first find out the length of the shape, and then you use calculus to find the area. I did it in calculus class. It's not fun. It's really not fun. But using this like physics-like theorem, Mamikon's sweeping tangent theorem, I kind of consider this physics. You can consider math as well. But if you move all the red, if you move all the, this time we're moving all the top green points together, because we're moving the points at the tangent location. Then we actually get a bunch of these curves, and they're equal in length because these green lines are all like the same unit vector. That's how we defined it. So the total area is just 1/4 of a circle. which is pi over 4. So that's a very easy way to find the length of the area in this region. And here we use the physics principle I'm using here is one, we have the Mamikon theorem, which is debatable that it's physics, and two, the velocity is tangent to the path. That's what I'm using here. Here, the green segment refers to the velocity. That's the direction the point is being pulled in. And the black path is just that. It's a path that it moves. And a very common concept in physics is that the direction you're being pulled in, like the direction you're moving in, sorry, your velocity, is instantaneously tangent to your path. So that's why we can use this Mamikon sweeping tangent theorem. So yeah, I thought this was cute. You probably won't realize why this is such a lifesaver until you actually do the calculus, but I think it's nice. Anyway, that's all they had. Well, that's not all they had, but we should probably stop here. We've gone over time. Thank you all for coming. I hope you've been interested in math and you can see the connection between math and physics now. So don't just go for one or the other. You should go for both. At least give them a try. Thank you all for coming. Have a nice day. See you all later. Bye.